At-Risk has a very powerful tool, its Simulation Scenarios tool, for discovering which uncertain inputs are most responsible for driving outputs to specified ranges of values, usually abnormally large or small values. The concept is fairly simple, but the way At-Risk implements this is more complex. This video will walk you through the procedure. Here is a model of sales of a new product. It is adapted from one of the At-Risk example files. There are several uncertain inputs in the cells with green font, and they lead to the single at-risk output, the NPV of profit, in the maroon font. A typical scenario analysis is the following. In a simulation of, say, 5,000 iterations, the NPV output will be above its 75th percentile in a quarter of the iterations, that is 1,250 iterations. In these 1,250 iterations, which of the inputs are most different from their values in all iterations? For example, when NPV is this large, does the initial unit cost tend to be abnormally small? Does the early annual demand growth tend to be abnormally large? Do any of the inputs in these 1,250 iterations tend to have about the same values as they have in all iterations? You can answer such questions by running the simulation, browsing the NPV output, and clicking the % button in the Browse Results window. This brings up the following choices. I will select the first. You then see this tornado graph. By the way, the results are highly dependent on the random numbers you happen to generate. You might see a slightly different tornado graph. In any case, the short story is that only two of the inputs, the product lifetime and the initial demand, are, quote, significantly different in the iterations where NPV is above its 75th percentile than in all of the iterations. In this case, they are both larger. The other inputs are not significantly different. The longer story involves at-risk's meaning of, quote, significant, and the numbers in the bars. For each input, this is based on three numbers: the median and standard deviation of the input in all iterations, labeled here as M1 and S1, and the median of the input in the iterations where the output is above its 75th percentile, labeled M2. If the absolute difference between M1 and M2 is greater than half of the standard deviation, the difference between medians is considered significant, and it gets a bar in the tornado graph. The percentage shown in the bar is the percentile where M2 falls in the distribution of the input for all iterations. For example, M2 for initial demand is at about the 70th percentile of the initial demand distribution. This is much higher than where M1 falls, which is at the 50th percentile by definition. The other number in the bar is M2 minus M1 divided by the standard deviation. That is, it is the number of standard deviations that M2 is above or below M1. For example, the product lifetime's median for large values of NPV is 1.11 standard deviations above its median for all values of NPV. Now you know the technical details, which you can revisit as necessary. The rest of this video focuses on the at-risk interface. First, you can drag any of the bars in the tornado graph off the window to get the following type of scatter plot. The blue points are where NPV is above its 75th percentile, and the red points are all iterations. This clearly shows that the product lifetime input tends to be larger when NPV is large. The blue points tend to be toward the right. Second, from the tornado graph window, you can click the % button and select Edit Output Scenarios to get the following dialog box. The three scenarios you see are the defaults, but you can change them in many ways. For example, you can select actual values And then for the first scenario, change this to less than $250,000. This is about the 8th percentile of the NPV distribution. Then the tornado graph changes as you see. In this case, 4 inputs are significant. The top 2 have lower medians for this scenario, and the bottom 2 have higher medians. In this case, the values shown in parentheses in the bars are the actual values. That is, the medians of the various inputs when NPV is larger than its 75th percentile. Third, you can click the % button below the Define Filters button on the At-Risk ribbon. This opens a highly interactive window with all the same options for specifying scenarios. It has 2 drop-downs at the top and a row of buttons at the bottom, and they are all quite straightforward. For example, if you click the middle button at the bottom, you see a matrix of scatter plots. Then you can drag any one of these off the window to see an expanded version of it. Finally, you can select scenarios from the Excel Reports button and you see essentially the same report as the one I just showed, but now it is in a separate worksheet window. This version isn't interactive. In summary, when you perform a scenario analysis in At-Risk, keep the big picture in mind. Although the details are somewhat complex, the goal is quite simple. You are trying to see which inputs are primarily responsible for an output being abnormally large or small. At-Risk has a number of built-in functions called property functions. You can see a list of these in the Insert Function drop-down list. All of these. There is no common theme to these various functions, so it is somewhat difficult to describe them as a group. You will typically see them when you add input distributions or when you add at-risk outputs. They are essentially tacked on to the input distribution functions or the risk output function, and they are typically used to describe the inputs or outputs in some way. As a simple example, suppose you select an output cell and click the Add Output button. This suggests a name for the output, but you can override it to say revenue. Then you will see that the function risk output of revenue has been added to the formula. However, there is another way you can do this. From the Add Output dialog box, if you click the FX button, you see this dialog. If you fill it in as shown, revenue, dollars, and I'll specify continuous, you see how risk output has been changed. The first 3 arguments of risk output are reserved for the name, the range name, and the position in the range, respectively. These latter 2 arguments aren't used here, hence the extra 2 commas. But the final 2 arguments you see are the property functions, risk units, and risk is discrete. In this case, their values will be reflected in at-risk output graphs and reports. Another use of property functions for an at-risk output is in a Six Sigma quality control setting. Suppose the output must be between lower and upper specification limits, LSL and USL, of 172 and 228, and it should have a target of 202. Then when you add the output, and click the FX button, you can give it a name and units, and you can click the Six Sigma tab and fill out the resulting dialog box as shown. Click OK, click OK, and you can see that now there is another property function, the risk Six Sigma function, with the arguments that I specified. There is also the units, risk units property function. Now I will run a simulation for that output. As you can see, the histogram of the output shows the specification limits, the target, the name, and the units. Property functions can also be added to input distribution functions, again to describe or modify them in some way. The easiest way to do this is by clicking the FX button to the right of the cell formula box in the Define Distributions window. There's the normal distribution. I will click the FX button to open this dialog box. I'll fill it out as shown. With these settings, the distribution formula changes as you see here. Now there are three property functions: risk name, risk units, and risk static. The name and units will appear in at-risk graphs and reports. The static value is the value you will see when the at-risk dice button is toggled to static. 99. Another important property function that can be used with input distributions is the risk cormat function. This allows you to induce correlations between various inputs. The easiest way to do this is through the Define Correlations button on the at-risk ribbon. Because this is such an important topic, it is discussed in more detail in the Correlated Inputs video in the guided tour series. You shouldn't feel obligated to memorize or even learn all of the available property functions in at-risk. Some are quite specialized, and you might never need to use them. However, you should at least be aware of property functions, and you should not be surprised when you see them tacked on to familiar input distribution functions and risk output functions. One area of particular interest to many analysts, particularly in a manufacturing setting, is quality control. The various methodologies that have been developed in the past few decades have been given many names and acronyms, but a particular favorite is Six Sigma. At-risk incorporates a number of common quality calculations with its collection of Six Sigma functions. You can see a list of them in the Six Sigma group under the Insert Function dropdown on the at-risk ribbon. All of these. This video will explain how to use these functions and what they mean. The example shown here is used to illustrate Six Sigma functions. This is for a process that makes parts. The parameters in cells C10 and C11 indicate how the process is producing normally distributed parts. Mean 100, standard deviation 0.5. A typical part diameter is generated in cell C18 with a risk normal function. The parameters in cells C3 to C7, especially the first three, indicate how the company would like to produce parts. They would like the parts to have an average diameter of 100, and they consider any part beyond the LSL and USL specification limits to be defective. The 0-1 values in cells C19 to C21 indicate whether a typical part is within specification limits. below the LSL, or above the USL. And these three cells have been designated as at-risk output cells. The process with these particular parameters is called a 3 sigma process because the mean of the process is 3 standard deviations from each specification limit. These values are indicated in cells C14 and C15. You would expect a 3 sigma process to produce very few defective parts because a normally distributed value has a very small chance of being more than 3 standard deviations from its mean. As the 6 sigma functions will indicate, however, a 3 sigma process is not necessarily as good as you might think. The key to using the at-risk 6 sigma functions is to append the risk 6 sigma property function with arguments in cells C3 to C7 to the risk output function when the part diameter in cell C18 is designated as an at-risk output. To do this, you select cell C18, click the Add Output button, click its FX button, and click the 6 sigma tab, and then you fill the dialog box out as follows. You refer to all of these cells, Actually, the italics indicate that these values are cell references, as you just saw. And the value in cell C7 actually has no effect on any of the results shown in this video. Its role is quite limited. You then see that the risk output function in cell C18 includes the property function, risk 6 sigma, with those parameters. This addition of the property function has 2 consequences. First, when you run the simulation and then browse the part diameter cell, you will see the LSL, target, and USL superimposed on the graph. There they are. And I will move the sliders so that they are at the specification limits. As you can see, there are very few defectives. Keep in mind, however, that the given LSL, target, and USL are fixed. They are engineering specifications for this part. However, if the company's process mean is off target and/or its standard deviation is larger, the picture won't be nearly this nice. Here is an example where I will change the mean to 100.5 and the standard deviation to 0.75. Now I will rerun the simulation. Again, the sliders are positioned at the specification limits, and you can see that there are clearly a lot more defectives, most of them on the high end. Now I will set the mean and standard deviation back to their original values. And I will rerun the simulation again. Look at the summary statistics in column F. The first 5 are nothing new. They simply apply risk mean and risk STD DEV, standard deviation, to the output cells. But from row 11 down, you see the second consequence of the risk 6 sigma property function. It enables you to use the 6 sigma functions. Their names are spelled out in column E. Each takes an argument, which is the part diameter cell. There are other 6 sigma functions besides these, but the ones shown here are the most common. Probably the two most common measures of quality are the CP and CPK indexes. The first of these, CP, is relevant for a process where the mean is on target, as it is here. It is scaled to be 1 for a 3 sigma process and 2 for a 6 sigma process. Larger values of CP are good and smaller values are bad. The CPK index is for a process where the mean is nearer to one spec limit than to the other. In this case, there is a CP type value for each limit, shown in cells C13 and C14. And CPK is the smaller of these. You will see an example shortly of such a process. The values in cells C16 to C18 are parts per million defective total, below the lower spec limit and above the upper spec limit. Similarly, the values in cells C19 to C21 are probabilities of defectives, either total, on the lower end, or on the higher end. Remember again that the numbers shown here are for a 3 sigma process. But even for this good a process, there are about 2,800 defective parts per million. This is why companies like Motorola decided that 3 sigma was not good enough. They strived for and achieved 6 sigma processes. But before seeing a 6 sigma process, change the mean to 100.5 so that it is closer to USL than to LSL and rerun the simulation. Now CP isn't relevant because the mean is off target. The relevant index is CPK, which is based on the distance from the mean to USL, the closest spec limit. And it is well below 1. Now the bad parts, and there are a lot of them, are on the high side. There is one famous number you might have heard in quality control settings, 3.4 defectives per million parts. This number arises from two conditions. First, the process is assumed to be a 6 sigma process. However, the second condition is that the mean might have shifted off target by as much as 1.5 standard deviations. The idea is that a shift of this magnitude might take a while to recognize. At Risk lets you simulate such a shift with its long-term shift parameter in cell C6. So for this example, you enter the mean and standard deviation as 100 and 0.25 to get a 6 sigma process, and you enter 1.5 as the shift. When you run the simulation, you get the results shown here. Specifically, you get approximately 3.4 defectives per million in cell F16. Any company that can achieve this level of quality is truly first-rate.